Hello, and welcome to the third clinic for linear algebra. In today's clinic, we are going to go over problem set number 3, and this problem set deals with the idea of a linear equation and systems of linear equations. This is probably going to be a review from basic algebra. Right. So first, we're asked to determine whether each of the following equations is linear and to explain the answer, right? So this equation, right, it's 5x plus 7y minus 8yz equals 16. So this is not linear, right? Because we have negative 8yz term. Right, so remember, to be linear, it has to be a single variable, and what you're being multiplied by is a constant, right? So it would have to be of the form, in this case, ax plus by plus cz is equal to some constant d. So x plus pi y plus ez is equal to log 5, right? Well, log 5 is definitely a constant, so that's satisfied. Pi is a constant, and actually so is e. Right? This is linear. And then 3x plus ky minus 8z is equal to 16. Well, this one actually depends. If k is a constant, then this would be linear. If k is not constant, then it would not be linear, right? So it really depends on what k is.
I have a question.
Yes.
So for C, if it depends on if K is linear, couldn't the same logic also apply to the first one? Like if maybe if either Y or Z is constant, or I guess if Z was a constant, wouldn't that make it linear?
If z wound up being some constant value, then yes. But typically, right, when we look at equations, we always think of x, y, and z as variables, which is why we just immediately jump to that not being linear.
Okay.
Right. Versus we typically look at k as a constant value in mathematics.
Oh, okay.
Right, so that's more of out of a convention. But yes, if either y or z was a constant, then that would be linear for part A.
Okay, got it. Thank you.
Right, we're now asked to determine whether each of the following is a solution to the given equation. So to be a solution, right, when you plug it in, the equation has to be satisfied. So much like with a single variant, right, a single variable equation. x1, x2, x3, x4. So that's how the ordered quadruple works. And when you plug it in, you do get 15, right? And 15 equals 15. So this is a solution. One and four is 5, minus 16, negative 11, plus 15 is 4. And that clearly is not 15, right? So this is not a solution to the equation. Don't know why I wrote out solution that time, but whatever. And so consider this system of two equations in two unknowns, right? We want to first determine the values of A for which the system has a unique solution. What I'm actually going to do is now delete some of these extra space. So for part A, let's do negative A times this first equation, right, and add it to the second equation. That's going to have the effect of canceling out the x terms, right? So we get 9 minus a squared times y is equal to b minus 4a. So this is going to have a solution. If and only if nine minus a squared is non-zero. Right? Because then we could just divide both sides by 9 minus a squared. We get y equals some value. We could do backward substitution to find the specific value for x. This, of course, means that a squared cannot equal 9. Right? Or a cannot be plus or minus 3. All right, so what we conclude is there exists a unique solution for all A, or I'm going to do it this way. There exists a unique solution for the set of all A. And I'll write in set notation. Set of all A such that A is not plus or minus 3. For part B, we want to find pairs A and B for which the system has more than one solution. Well, we again travel back up, right, to when we added negative A times the first equation plus the second equation. Say there's multiple solutions. When both sides are 0, right? So when 9 minus a squared is 0, and then b minus 4a is 0. Well, good news is we already know when 9 minus a squared is 0, right? That means a has to be plus or minus 3. So now what we do is take one of the values. Let's start with positive 3. Plug it back into b minus 4 equals 0 and solve for b. That means b has to be 12. All right, now do the same thing if a is negative 3. And that means b is negative 12, right? So therefore, there are multiple solutions. For 3, 12, and negative 3, negative 12. Now we want to solve a system. In algebra, it is taught that the method to solve a system of linear equations is called the method of elimination, right, or systematic elimination. Right. What that entails is trying to cancel out as many of the unknowns as possible, and then use backward substitution. Right. We do this using elementary operations. Looks like the x is going to be very easy to get rid of. So I'm going to multiply the first equation by negative 1, add it to the second. All right, so that gives us 3y minus 5z is equal to negative 6. Why did I do negative 1? It should have been negative 2 times equation 1. Oops. That's better. They drop out. This is what? Negative 4. So y minus z is negative 2. All right, let's call that new equation 4. Now let's do -3 times equation 1 plus equation 3. Again, the x's drop out. -8y plus 15z is equal to 23. All right, we'll call that equation number 5. These two systems are equivalent systems, meaning they have the same solution. Now let's try and cancel out that y. All right, well, if multiply equation 4 by -8, add it to, not -8, +8. I need more coffee. And add it to equation number 5, right? We're going to get rid of the y's, yeah? So they drop out. We get -8z plus 15z, that is 7z. So -16 plus 23 is 7. We'll call that equation 6. Right, so this system is equivalent to this system up here, which is equivalent to this, the original system. So all three systems have identical solutions. From down here, we can conclude that z has to be 1. Now do backward substitution. Let's plug that into equation 4. So y minus 1 would have to be -2, meaning that y is -1. Now take both of those, plug them into one of the original 3. That first one probably be the easiest. And we'll wind up with x equaling 2. So our solution is the ordered triple, 2, -1, 1. Right. 5. Another system of 3 and 3. And so again, just to try and keep track, let's label each equation. Let's do 3 times equation 1 plus equation 2. That'll get rid of those. 7y minus 11z equals -10. Call that number 4. Now let's do -5 times equation 1 really. And then plus equation 3. Negative 10 plus 3 is negative 7y. (15 minus 4 is 11 plus 11z. 5 plus 2 is 7. And we'll call that equation 5. This is a contradiction. If we multiply equation 4 by negative 1, you get negative 7y plus 11z has to equal negative 10. I'm sorry, equal positive 10, right? The same value, basically what you're saying is 10 is equal to 7, which is nonsense. So the system is inconsistent. So there is no solution, right? So we say that the solution set is the empty set. It's empty. Let's do negative 2 times the first equation plus the second equation. Negative 4 plus 5 is 1, so we get y. 6 minus 8, we get minus 2z is equal to 2. Right, then it'll be negative 3 times the first equation plus the third equation. Get rid of the x's. Negative 6 plus 8, we get 2y. 9 minus 13 minus 4z. Negative 3 plus 7 is 4. So notice that equation number 5 here is 2 times equation number 4, right? These are the same. So what we can actually do is just ignore one. And so let's ignore the fifth equation. Therefore, what we have is y minus 2z is equal to 2. Meaning that y is 2 plus 2z. Right, so z is an independent variable in this case. That means we can let z be any real number we want. Y depends on the value of z. So let's say that z is equal to some real number r. Then y would be 2 plus 2r. All right, let's plug them into one of the original 3 equations. The first one is probably the easiest. Right, so we said y was 2 plus 2r. Right, so that has to equal 1. We get what? X plus 4. Plus 4r minus 3r is just plus r. That has to equal 1. So x would be negative 3 minus r. Right? Or if you wanted to, you could write it as negative quantity 3 plus r. Therefore, our solution set is the set of all ordered triples. Let's call it negative quantity 3 plus r, then 2 plus 2r and r, such that r is any real number. Right? So r is some arbitrarily chosen real number. So these are the 3 cases when you have a system of equations, right? You can have a unique solution, as we did in number 4. You can have no solution, as we did in number 5. Or you can have an infinite number of solutions, as we did in number 6. Those are the only 3 possibilities. Right? You can't have a system, for instance, that has only 3 solutions. If it has 3, it has to have an infinite number. So number 7. Solve the system. All right, so here we have a 3 in 5, right? So a 3 by 5 system. Which one looks easiest? Well, it looks like the x1 is probably going to be really simple to eliminate. X4 is also as simple to eliminate. I'm just going to stick with what I did. I'm going to eliminate the x1s first. All right, so negative 3 times equation 1 plus equation 2. Ups out, we get 9 minus, oh, good. The x2s are going to drop out. Negative 6 plus 7, so we have an x3. Plus 2x4. Minus x5 is equal to 1. Call that equation 4. Okay. Now it's negative 2 times equation 1 plus equation 3. Why don't you slide all the way over there? Go away. So again, x1s drop out. 6 minus 6, the x2s also drop out. That's really nice. Negative 4 plus 7 is 3x3. 2 plus 4 is 6. Minus 9x5 is equal to negative 4 plus 7 is 3. Did I screw up the previous one? I did. Negative 6 plus 3 is positive 3. Yeah, that should have been a plus 3x5. Now notice that 5 is a multiple of 4, right? Which means it's redundant. We can just get rid of it. Well, we just wrote x3 in terms of x4 and x5, right? So x4 and x5 are now independent variables. They can be anything we want them to be. I don't know why I did x3. That's x4 be r. Let x5 be t. Then what we're going to get is, let's plug that back in to the first equation. So what do we get? X1 minus 3x2 plus 2 times 1 minus 2r minus 3t minus r plus 2t is equal to 2. All right, so we distribute the 2 through. Right? Let's combine. So negative 4r minus r, that's going to be minus 5r. Negative 6t plus 2t would be negative 4t, right? So x1 would be, subtract out the 2. You get 3x2 plus 5r plus 4t. x2 is also an independent variable. Solution set. It's going to be an ordered quintuple. 3, let's pick. What variable do I want to use for x2? Q. Let's use Q. 3q plus 5r plus 4t. We already said x2 is q. We say x3 was 1 minus 2r minus 3t. x4 is r and x5 is t. Such that q, r, and t are all real numbers. So number 8. So this is a what? 3 by 4. Again, x1 looks really easy to eliminate, so let's go ahead and do that. Gets rid of that, right? So we get what? Negative 4 plus 5 is x is just 1, so we get x2. 6 minus 2 is 4. Negative 8 plus 1, negative 7. So negative 4 plus 1 is 3, so that's going to equal 3. Negative 3. So negative 10 plus 12, 2x2. 15 minus 7, so plus 8x3. Negative 20 plus 6, so minus 14x4. Then we get negative 10 plus 3, negative 7. This leads to a contradiction. multiply the equation 4 by 2, right? You get the left-hand side of equation 5 is equal to -6, right? So what these two equations are saying is -6 is equal to -7, which is nonsense. So we have no solution. So this is going to be the same as what we did in, what was it, number 3, except now we have a 3 by 3. So if we eliminate x, right, it'll be -2 times the first plus the third. So -4 plus 7 is 3y. -2 plus a is a minus 2 times z, right? So then that has to equal b minus 6. And this equation, right, the second one's just going to drop through. Try to get rid of the y's. And I'm going to label these because it's going to get a little complicated. I'm going to multiply the first equation by -a/3 and add it to the second. That gets rid of the a's. So this is the equation that we're left with. Let's get rid of the fractions. All right, so let's multiply by 3. This will have a unique solution. If and only if right, the coefficient of the z is not 0. Right, so this means we have -a² I'm sorry, that should be a 15 because I multiplied by 3. Negative a squared plus 2a plus 15 can't be 0. Multiply through by a negative, right? A squared minus 2a minus 15 can't be 0. That can be factored, right? We get a plus 2, no, a plus 3, a minus 5 can't be 0. So what we get is the set of all a such that a does not equal negative 3 and a does not equal positive 5. All right, part B. This has many solutions if and only if both sides are 0. So that is 15 minus a times a minus 2 is 0, and 30 minus a times b minus 6 is 0. Well, again, we already know. Right, that if 15 minus a times a minus 2 is 0, then a is either negative 3 or a is positive 5. If a is negative 3, just plug it back in. So we get 30 minus negative 3 times b minus 6 equals 30 plus 3b minus 18, which is 12 plus 3b, and that has to be 0. Does that mean that b would have to be negative 4? Likewise, if a is equal to 5, we get 30 minus 5b plus 30, right? Or 60 minus 5b has to be 0. And so doesn't that mean b would have to be negative 12? I'm sorry, positive 12. So we get two ordered pairs, right? We get negative 3 and negative 4, and then 5 and 12.